Okay. Screen adjustable.
around in class. I'm in class, see? I've talked to him.
So, good afternoon. I hope you are able to join this lecture. Okay, so I'm still waiting for the numbers to increase a little bit, then I'll continue. So just give me 1 or 2 minutes. Wait for your colleagues to join. Okay, so in the morning we looked at relative atomic mass, relative molecular mass, and relative formula masses, their definitions, and how you calculate them. You also looked at empirical formula and molecular formula. Okay. We looked at percentage composition and calculation of percentage composition from empirical formula data. Okay, so I'm just trying to work out the live chat. I can't see your comments, so that's why I keep moving the slide so that I'm able to see what you're commenting. Okay. Right, so we are now going to look at combustion analysis. Okay, did we have people who attempted these questions? Okay, so on combustion analysis, each time when you are analyzing organic compounds, And these are compounds which have carbon, hydrogen, and sometimes oxygen. Okay. We use a device which is known as a combustion device. Okay. And basically, what you do is you burn your sample in the presence of oxygen, and this converts all its carbon to carbon dioxide and all its hydrogen to water. Okay, so you get your unknown sample, you place it in the device, and you place it in the device, and you burn it, and then what the information you get gives you data which can help you to actually calculate empirical formula. Okay, so the data given allows an empirical formula determination with just a few more steps. Okay, so what you get are the masses, because each time you burn an organic compound, it will give you carbon dioxide and water. So you have the products. So the mass of the products, which is carbon dioxide and water, will be known. So we work our way backwards for you to know the mass of that unknown compound. Okay, so by definition, combustion analysis is the technique of finding the mass composition of an unknown sample X by examining the products of its combustion. So you have an unknown compound which is X. When you burn X in excess oxygen, it will give you carbon dioxide and water. So X is unknown, but the products are known. Okay, X is unknown, but the products, which is carbon dioxide and water, is known. So you can probably just, by using the masses of the products, you can work backwards to determine the mass of the unknown compound X. Okay, so to look at as a calculation, we can look at this sample question. Suppose that 0.250 grams of compound X was burned in a combustion device and produced 0.686 grams carbon dioxide and 0.562 grams water. Determine the molecular formula and empirical formula of X. Okay, so what we'll do is I'll show you two methods. The first method utilizes several steps. So step one is you find the mass of carbon and hydrogen that must have been present in X. Okay, you find the mass of carbon and hydrogen that must have been present in X. Remember, we have the masses of the products, which is 0.686 grams carbon dioxide and 0.562 grams of water. Okay, what we want is to work backwards to determine the empirical formula of X, empirical and molecular formula of X. So step one, like I've mentioned already, you find the mass of carbon and hydrogen that must have been present in X. So all you do is we start with the, since this is an organic compound, so we know that the atoms which are obvious, okay, because an organic compound consists of carbon and hydrogen. Okay, so we know that the elements which are obvious, which are present, is carbon and hydrogen. So we start by determining the mass of carbon. So all you need to do is you multiply. Okay, so you get the total mass. This carbon is in carbon dioxide. So you need to determine the mass of carbon in carbon dioxide. Okay, so the mass of carbon in carbon dioxide, you multiply. Okay, so how many moles? Okay, how many moles of carbon dioxide are present? So it's 1 mole of carbon dioxide which is present, as we can see. So divide that by the molar mass. So it's 44.01 gram per mole of carbon dioxide. Okay, multiply that with how many moles of carbon are in carbon dioxide. So there is 1 mole of carbon in 1 mole of carbon dioxide. Okay, so of course it may look confusing by the first impression, but as we move on, it will actually clear up. Okay, so we'll move slowly so that people are able to follow. Okay, so I said get the total mass of carbon dioxide, which is 0.686 grams. This 0.686 grams is there in the question. This is what was produced. Okay, then what is our interest? Our interest is to determine the mass of carbon in carbon dioxide, because this mass of carbon is what was present in X. Okay, that's a mass which was present in X. All right, so
And I'm in class, so just come through. I'm having an online class. Just come through with the first door.
okay, sorry about that break in transmission. I think it's network. Okay, so 0.686 grams carbon dioxide, you multiply that with 1 mole of carbon over the molar mass of carbon, which is 44.01 gram per mole, times, okay, so in carbon dioxide, there's 1 mole of carbon, so you multiply that component. Then times, what is the mass of carbon in that 1 mole of carbon dioxide is 12 grams per 1 mole of carbon. Okay, that will give you 0.187 grams of carbon. Okay, then when you go to hydrogen, how do you determine the mass of hydrogen? Get the total mass of, because this hydrogen is in water. Okay, so you have to get the total mass of water. So it will be 0.562 grams of water times how many moles of water are present? There's 1 mole of water over the molar mass, which is 18.02 gram, times how many moles of hydrogen are in this water. So if you look here, there are 2 moles of hydrogen in this water. Okay, there are 2 moles of hydrogen in 1 mole of water. And what's the mass of those 2 moles of hydrogen? The mass is actually 2.00 gram per mole. Okay, so that will give you the mass of 0.063 grams. Okay, so the other way you do work those out is by, okay, so I'll just try to write something. If okay, so I'll try to write down something here. If we want to determine the moles of carbon, so moles of carbon, sorry, actually it's mass of carbon. Mass of carbon will basically be, if you look back on this slide, we are saying you look at you look at the total mass. Okay, total mass of carbon. So this carbon is actually obtained from carbon dioxide. So this mass of carbon is actually obtained from CO2. Okay, it's obtained from CO2. So it's obtained from CO2. Okay, so this basically means so you get the total mass, which is 0. So this is 0.686. Okay, that is the total mass of carbon. Okay, if you got your question, if you got your question very well, so it will be 0.686 times, okay, this is grams, by the way. So this will be times. Okay, so now how many moles of carbon are in carbon dioxide? Of course, it's 1 mole. 1 mole of carbon present in 1 mole of carbon dioxide. Okay, and then what's the mass? Okay, mass of carbon is actually 12 grams. So I'll just insert something here. So this is another way. So if you find this one is simpler for you, you're free to use it. 12 grams of carbon in the total mass. So what's the total mass of carbon dioxide? It's basically 44 gram per mole. Okay. So if you do this calculation, 12 over 44 times 0.686. Okay, so we can just do that calculation. We compare if we have the same answer. So 12 over 44 times 0.686. We are getting 0.187, okay, grams. So in this mass, okay, so what this means is in this mass, in 0.686 grams, there is 0.187 grams of what? Of carbon. Okay, it means we have now determined the mass of carbon in this carbon dioxide. Okay, if you compare, let's go back to our previous slide. Okay, you're able to see that actually okay, so able to see that the answer which was obtained using this first working is actually 0.187 grams. And if we use this second method, we are getting 0.187 grams. Okay, so we can go now to hydrogen. Let us determine the mass of hydrogen. We follow this same method. So mass of hydrogen is actually obtained from is obtained from water. Okay. Sorry, my pen is not the battery is actually flat. That's why I'm now struggling to actually write, but I'll try to type the way I'm typing. So mass of hydrogen is obtained from water. Okay. And then for you to determine this mass of hydrogen, you multiply. Okay, so how many moles of water, how many moles of hydrogen are in 1 mole of water? There are actually 2. So it will be 2 point, because we know that the atomic mass of hydrogen is 1.01. So it will be 2.02. 2.02. Okay. So here you refer to the class we had in the morning. Atomic mass of hydrogen is 1.01, and since there are 2 of them, you multiply that by 2, and you get 2.02, okay, grams. So that's where this 2.02 is coming from. Okay. So I insert something, insert an equation, so it will be 2.02 grams over the total mass of water. Total mass of water is actually 18.02. Where did we get this 18.02? Okay, so you add. Okay, so we are here. You get you add atomic mass of hydrogen. Atomic mass of hydrogen is actually there are 2, so it will be 2. So it will be 2 times 2.02, then plus oxygen from the periodic table is 16, so plus 16. Okay, and there's only 1 atom of oxygen. Okay, so when you add that, you get that 18.02. Okay, right. So you get the mass of hydrogen, which is 2.02 over the total mass, which is 18.02. Then that one multiply with the total. What's the total from the question? Total mass of water is 0.562 grams. Okay, 0.562 grams. So you multiply that by 0.562 grams. Okay, so we can do that calculation for those who have got calculators. It will be 2.02 divided by 18.02, then times 0.562, you get 0.0629, okay, which when you round it off, you get 0.063. Okay, 0.063. Okay, so now we can check with what was obtained using the first method. This is the first method. So the mass of hydrogen is actually 0.063 grams. Okay, so these are the 2 methods, whichever you are comfortable with. So this method is actually there in Zumda. You can check it out. You can also use this second method. So this is the second method. Okay, so I will just write there second. That's the second method. So whichever you are comfortable with, you can use. Okay, so now we have obtained the masses of these. Okay, remember our question is, we have this unknown compound X, which we want to know its molecular and empirical formula. So using the method of combustion analysis, you burn it in excess oxygen. Okay, so we can burn it in excess oxygen, and by burning it in excess oxygen, we are basically just reacting it in excess. Okay, so it will appear like that. Okay, then when you burn it in excess oxygen, what are you going to have? You're going to have carbon dioxide and water. So, and that is what we have there. Okay, so we have carbon dioxide plus carbon dioxide plus water. Okay, carbon dioxide plus water. Okay, so we know the mass of carbon dioxide because this is the mass of carbon dioxide. We know the mass of water. This is the mass of water. Okay, but what is our target, or what is our task? Our task is to determine the masses of carbon in carbon dioxide and the mass of hydrogen in water. Okay, because these two elements, carbon and hydrogen, are contained in the organic compound X. The moment you determine their masses, it means you'll have obtained their actual masses from the starting material. Okay. Right. So having found those masses, we now proceed to determine the empirical formula. So the next step is you find out if there's oxygen or unknown compounds in X. Okay, so the step one, for those who are a little bit lost, step one was what? Step one was find the mass of carbon and hydrogen that must have been present in X. Okay, and I've shown you the two methods of determining the mass of carbon and hydrogen that would have been present in X. So this is method one, which is on display, and this is the method two, which is there. Okay, then step two is find out if there's oxygen or unknown compounds in X. Okay, so all you need to do is, since you now know the masses of carbon and hydrogen, okay, since you now know the masses of carbon and hydrogen, you now subtract their masses from the mass of the original compound X. If you go back to your question, it says that suppose that 0.250 grams of compound X was burned in a combustion device, giving you those products. So we have this original mass of compound X. Okay, we have this original mass of compound X. So you subtract 0.250 grams minus the two masses, the mass of carbon and the mass of hydrogen. So when you add up these two masses and you subtract from 0.250, you get 0 grams. Okay, you get 0 grams. So it means that compound X must contain only carbon and hydrogen only, and no oxygen. Okay, and no oxygen. Right. So since there's no oxygen, we are now clear that our compound only has carbon and hydrogen. We now proceed. Okay, so step 2 states that find the number of moles of carbon and hydrogen. So finding the number of moles of carbon and hydrogen, we basically use the same method, the same steps we were using when determining empirical formula. Okay, so remember, when we're looking at empirical formula determination, we said convert all the given quantities to moles. Okay, so here basically you just say number of moles is equal to mass over molar mass. Okay, so for carbon, the mass is 0.187 grams. Divide that by the molar mass of carbon, which is 12.01, you get the moles as 0.0156 moles. Okay. Then for hydrogen, the mass is 0.063 grams. So using your same formula, number of moles is equal to mass over molar mass. Okay. So for those who may be lost, well, the formula we are using is we are using moles. So I'm just typing it down here so that you are able to see it. So it will be moles is equal to mass over molar mass. Okay, so that's the formula we are using. And then the mass of carbon here is 0.187, so it will be 0.187 grams over the molar mass of carbon is 12. Okay, 12.01 gram per mole. Okay, and when you do that division, this is what we are getting here. We are getting 0.0156 moles. Okay, so you use the same formula to determine the moles of hydrogen. Moles of hydrogen is equal to mass over molar mass. The mass is 0.063 grams over the molar mass, which is 1.01 gram per mole. Okay, so you get your moles as 0.063 moles. Okay, so you can give me 1 minute. I try to check your comments here. Let's see. Okay, so I'm back. Thank you for your patience. Okay, so we now have the moles there. Okay, then we go to step 3. So step 3, you now find the simplest mole ratio by dividing. You divide by the smaller number of moles. So for those who are following, you're able to see that from step 2 going downwards, we're just using the formula for empirical formula determination. Okay, the only new concept which has been added here is the concept of combustion analysis, where we are now determining the masses of carbon and hydrogen present in X. Okay, so from step 2 going downwards, we're just following the same steps we used in empirical formula determination. All right. So now that we have the moles, you now have to determine the mole ratio. The mole ratio, look at the smaller number of moles and divide it throughout. So we notice that the smaller number of moles here is 0.0156. So divide 0.0156 over 0.0156, you get 1. Then 0.063 divided by 0.0156, you get 4. Okay? So it means that our compound, remember our compound has only carbon and hydrogen, and the mole ratio has been determined as carbon is 1, hydrogen is 4. It means that our formula now is CH4. Okay, our formula now is CH4. Okay, so this is the basic steps you need to follow when calculating. These are the basic steps you need to follow when calculating empirical formula. Okay. So the summary of all this is the first thing when you are doing a combustion analysis problem, the first thing is you need to find the mass of carbon and hydrogen in the sample. Okay, and I've given you two methods of determining the mass of carbon and hydrogen in the sample. Step 2 is find the actual number of moles of carbon and hydrogen in the sample. So meaning you just need to convert the mass determined, convert it to moles. Okay, then step 3, find the relative number of moles of carbon and hydrogen. Okay, so by finding relative number of moles, you are simply dividing by the smaller number of moles. Okay, then after that you need to write the empirical formula for the known compound. Okay, so we can look at another question, okay, so that we are able to follow what is basically happening here. Okay, so I'll pick on one question here. Probably we can look at question 1. And this is the second sample question. Combustion of 0.255 grams of fuel containing carbon, hydrogen, and oxygen produces 0.561 grams of carbon dioxide and 0.306 grams of water. Okay, so determine the empirical formula. Okay, that would be the problem there. Okay, you need to determine the empirical formula. Okay, so we use the same method. You can use method 1, where you multiply the masses. Okay, you multiply the total mass by the mole ratios. Okay, so 1 mole of carbon dioxide has molar mass of 44.01 gram per mole. Okay, and in this we have 1 mole of carbon, okay, which has a mass of 12 grams. Okay, you can use that method or simply use the method I introduced as method 2. So if we have to use that one for the sake of time, okay, so compound X is reacting with oxygen, so that's basically combustion, oxygen to give you carbon dioxide, plus water. Okay, so this is a basic chemical reaction for combustion. Okay, and we don't know the molar mass of X, so we don't know the empirical formula of X. Okay, but we do know the quantities. So for carbon dioxide, we have 0.561 grams. Okay. Then for water, we have 0.306 grams. Okay, so we need to use these quantities to actually help us determine the masses of carbon. So in this compound X, we are sure, because now the question is clear, we have carbon and hydrogen. So we have carbon, hydrogen, and oxygen. Okay. But what are the quantities for carbon? We don't know. So that's X. Okay. Okay, so carbon there is X, hydrogen is Y. We don't know how many atoms of hydrogen are there, and oxygen there we can say Z. Okay, so what is our task? Our task is to work out these quantities. What is X, what is Y, what is Z? The moment you work out these quantities, that is what will give you the formula for this organic compound X. And how do you determine these? This carbon can only be determined by knowing how much of it is contained, because this carbon has been produced in carbon dioxide. This hydrogen has been produced in water. So it is these quantities which are here which will help you determine the masses of carbon and hydrogen present in X. Okay, present in X. So using the same methods, one of the two methods I've shown you, okay, sorry, we'll now look at carbon. So let us find the mass of carbon which is present in X. So mass of carbon in carbon dioxide. Mass of carbon in carbon dioxide is as follows. So you multiply, the total mass is 0.561 grams times okay, so you look at how many more, okay, what's the mass of carbon present in carbon dioxide? So it's 12 grams of carbon present in 44 grams of carbon dioxide. Okay, 44 grams of carbon dioxide. Okay. And when you do that calculation, 12 over 44. So for those who've got a calculator, you can work this out as well. So it will be 12 divided by 44 times 0.561. You get 0.153, okay, grams. Right. So we have now determined. So in 0.561 grams of carbon dioxide, there is 0.153 grams of carbon. Okay. Then we can work out for water now. So mass of hydrogen in water will basically be the same. So we only change the mass here because now we are putting the mass of hydrogen there. So it will be 0.306 grams. Then we change what's the mass of hydrogen. It is actually 2.02 over the mass of water. Molar mass of water is 18.02 grams. So here it will be carbon, it will be hydrogen, and here water. Okay, so then we now work out 2.02 divided by 18.02 times 0.306. You get 0.0343, okay, grams of hydrogen. Right. So in 0.306 grams of water, there is only 0.0343 grams of hydrogen. Okay. So from this step now, the next thing we need to do is we now follow this follow the steps, okay, for empirical formula. Follow the steps for empirical formula determination. Okay, empirical formula determination. Okay, of which step 1 is convert your given quantities to moles. Okay, and then step 2 is do a mole ratio. Okay, but since this organic compound does not only contain carbon and hydrogen, it also contains oxygen. So we need to know the quantities of oxygen. Okay, so mass of oxygen, you just subtract the two masses. You subtract, so the mass of oxygen will basically be the total mass of the fuel, which is 0.255 minus 0.1153 plus 0.0343. Okay. So that will give us the mass of oxygen. You subtract the sum of the mass of carbon and hydrogen, you subtract it from the total mass. That being the case, then it will be 0.255 minus 0.153 plus 0.0343. Okay, and that will give us 0.0677. Okay, that's the mass of oxygen. Mass of oxygen. Okay, so from there onwards, we now follow the empirical formula determination like I mentioned. So by empirical formula determination, you basically just convert these quantities to moles. Okay, so using the formula like I mentioned, using this formula, number of moles is equal to mass over molar mass. Okay, so put it there. Mass, okay, so molar mass is equal to mass over molar mass. Then we start with the moles of what? We start with the moles of carbon. Okay, moles of carbon is equal to mass over molar mass. And what's the mass of carbon? The mass of carbon we have found is 0.153. So 0.153 grams over the molar mass. The molar mass of carbon is 12 grams per mole. And that will give us the moles. Okay, so we just simply divide 0.153 divided by 12, and that will give us 0.01275. Okay, moles. We now find the moles of hydrogen. Moles of hydrogen will basically be mass over molar mass. The mass of hydrogen found is what? So we go back to the slide. So it will be 0.0343. 0.0343 grams over the moles of oxygen. Sorry, the moles of hydrogen is 1.01. So we put 1.01. Okay, so basically have the same number. Okay, so it will be 0.0343. Okay, then we now move on to the moles of oxygen. Moles of oxygen is equal to mass over molar mass. And what's the mass of oxygen? Mass of oxygen is 0.0677. 0.0677 over 16, which is the molar mass of oxygen, and the moles will be 0.0677. So it will be 0.0677 divided by 16. You get 0.0042423. Okay. Right. So now we have converted all the given quantities to moles. Okay, the next thing is you just have to divide by the smaller number of moles so that you get the mole ratios. Okay, so that you get the mole ratios, and the smaller number of moles here is basically 0.00423. Okay, so we'll divide throughout so that we get the mole ratios. So we get the first one. So for oxygen, it is actually 0.01275 over. So we are dividing everything by the smaller number of moles. So it will be 0.00423. Okay, and if we do that division, so it will be 0.01275 divided by 0.00423. We are getting 3.33, which is 3.01. Okay, which is just 3. Okay, then we go to the next one, which is the for hydrogen. So hydrogen, it will be 0.0343 over the smaller number of moles, which is 0.00423, and that will give us 0.0343 divided by 0.00423. We're getting 8.1. Okay, then we go to the last one. The last one will basically give us 1. Okay, 0.00423 over the same 0.00423. Okay, that will give us 1. Right. So now we have the mole ratios. So the next thing we need to do is remember our target. So our target was to determine what X is, what Y is, and what Z is. Okay, so it means we just need to divide. So in this case, so since this division is for carbon, it means here, so if I was to write it properly, I can write it properly for you. So it will be carbon. Carbon in this case, X is 3. Then hydrogen. Hydrogen in this case is 8. And then oxygen in this case is 1. Okay, so you don't even indicate it, just leave it. Right, so that gives us the empirical formula of the compound. Okay, that gives us the empirical formula of the compound. So meaning the empirical formula of this compound is basically C3H8O. Okay, right. So that's how we actually determine the empirical formula, and I hope it's clear. Those who would want to use the first method are free to do that, and those who would want to use this second method are also free to do that. Okay. The next outline is determination of the mole. So here we'll look at what the mole is, what Avogadro's number is. We look at quantitative information from balanced reactions. We look at limiting reactant, theoretical yield, percentage yield. Okay. So let us look at what mole is. The number of moles of a chemical is its amount. So 1 mole of a substance equals the amount that contains Avogadro's number of atoms or molecules. Okay, 1 mole of a substance equals the amount that contains Avogadro's number of atoms or molecule. 1 mole of an element or molecule has a molecular weight of that element or molecule expressed in grams. So for example, let us look at the molecular weight of glucose. Glucose has formula C6H12O6. If you want to determine the molecular weight of glucose, you multiply relative atomic masses of the given constituents times the number of atoms. So we go to carbon. So carbon, there are 6 carbon atoms. Multiply that by the relative atomic mass, which is 12, plus there are 12 hydrogen atoms times the relative atomic mass of hydrogen, which is 1, okay, plus the number of oxygen atoms is 6 times relative atomic mass, which is 16. When you add that up, you get 180 gram per mole. Okay, so you get this from actually Zumda chapter 3, the 3rd chapter. Okay, so looking at molar mass still, we now look at the definition. So by definition, these are mass of 1 mole of a substance. No wonder when you look at this answer, this is the molar mass here is 180 gram per mole. 180 gram per mole. So meaning molar mass is mass of 1 mole of a substance. Mass of 1 mole of a substance. The molar mass of an element is a mass number for that element that we find on the periodic table. The formula weight will be the same number as the molar mass. I think I already clarified in the morning the difference between molecular mass and formula mass, or molecular weight and formula weight. Okay, so please we use this similar distinction here. Okay, so how does the aspect of Avogadro's constant come in? Okay, so Avogadro's number is a number of carbon-12 atoms in exactly 12 grams of carbon. And Avogadro's constant is normally given a symbol Na, and is given the number 6.02 times 10 to the power 23. Okay, that is the Avogadro's constant or Avogadro's number. This is the number of carbon-12 atoms in exactly 12 grams of carbon. Okay. So this number is very important. It helps us to determine the number of atoms, molecules, ions, or particles present in a given substance. Okay, so this Avogadro's number, it will help us to determine number of particles. So these particles may be molecules, atoms, ions present in a given substance. Okay, so because it's basically so for instance, if you're looking at moles, how many if you're looking at molecules, how many molecules are present in a given substance? So you basically say 6.02 times 10 to the power 23 molecules present in 1 mole. Okay, so that's the importance of Avogadro's number. Okay, let us look at a sample question to see the importance of using Avogadro's constant. Isomyl acetate have the formula C7H14O2. Okay, isomyl acetate have the formula C7H14O2. Calculate A, how many moles, and B, how many molecules are contained in 0.250 grams of isomyl acetate. Okay, calculate A, how many moles, and B, how many molecules are contained in 0.250 grams of isomyl acetate. Okay, so we'll look at how to determine. We start by looking at A. A is asking how many moles are present, okay, in 0.25 grams of isomyl acetate. Okay, so for us to determine how many moles are present, we basically need to calculate the molecular weight. Okay, we need to calculate the molecular weight of this substance. Okay, and how do we determine molecular weight? We need to sum up, multiply the atomic masses of each of the atoms present. Okay, multiply the number of atomic substances present. So like for instance, carbon is 12, multiply that carbon by 12 plus hydrogen, there are 14, multiply that by 1.01 plus oxygen, there are 2 atoms of oxygen, multiply that by 16. So the total sum was what will give you the molecular weight. Okay, so since we have the this compound, so we'll get it so that we determine so this will basically be so this will basically be 7 times, okay, to basically be 7 times 12 plus 14 times 1.01 plus 2 times 16. Okay, so if we do that calculation, that will give us the molecular weight. So it will be 12 times 7, that will be 84. 12 times 7 plus 14 times 1.01 plus 2 times 16. So it will be 130.14 gram per mole. Okay, so that will be the molar mass of this substance. Now the question is, how many moles are present in there? Okay, so we use our formula: moles is equal to mass over molar mass, okay, which is quite straightforward because you have been using that from your high school. Moles is equal to mass over molar mass. Then that would be the mass. So the question is, how many moles are present in 0.250 grams? So the mass is 0.250 grams over the molar mass is what we're just from finding is 130.14 gram per mole. Okay, and when you divide 0.250 divided by 130.14, you get 0.0019192. Okay, that's for part A. So the how many moles are present is basically 0.00192 moles. Okay, and then part B, how many molecules are contained in this same amount? Okay, so this is where now we use the empirical formula. Sorry, this is where we use the Avogadro's constant, and we know that 1 mole contains 6.02 times 10, 6.02 times 10 to the power 23. And what are they asking us? Molecules. So I told you Avogadro's constant helps you to determine how many particles are present. So these particles can be atoms, molecules, ions, and so on and so forth. Right. So 1 mole contains those molecules. What about, okay, what about 0.00192 moles? Okay. So what about 0.00192 moles? Okay, so meaning we're basically, so this will give us, of course, this question mark. So you just basically cross multiply. So 6.02 times 10 to the power 23. So it will be 6.02 times 10 to the power 23 times 0.00192. Okay. So I'm getting something like 1. Our x there is basically 1.15, which is 1.16 times 10 to the power 21. Okay, so can you please verify those numbers for me? So that we move on the same page. Okay, so that's how we determine, that's how we use Avogadro's constant to help us determine the number of atoms, molecules, or ions in a given substance. Okay. The next aspect is for us to understand what balanced chemical equations are. So balanced equations allow chemists and chemistry students to calculate various amounts of reactants and products. The coefficients in the equation are used as Mohr ratios. Chemical reactions tell us three things. Okay, what atoms or molecules react together to form what products, how much reactant and how much product is involved, and it also tells us the state of each species. Okay, so this is an example of a chemical reaction or chemical equation. It has reactants on your left hand side and products on the right hand side. So we have got capital letters A, B, C, and D, where A and B, capital letter A and B are your reactants, and capital letter C and D are your products. Small letters A, B, C, and D, they stand for the stoichiometric coefficients, which are also used as Mohr ratios. Okay. So many Mohr ratios can be written from the equation. For instance, let us look at the synthesis of urea. Urea is synthesized by reaction of ammonia with carbon dioxide. Okay, so you see that in the stoichiometric coefficient on ammonia is 2. So that also is used as a Mohr ratio. Right. So sorry, the live chat is disabled, so I'm not actually able to see your comments, but through your reps you can always be communicating with me. I think there was a concern of the screen, and I think I've adjusted it. Okay, so I was saying stoichiometric coefficients can also be used as mole ratios. Okay, so for instance, you can look at this synthesis of urea. How many moles of urea could be formed from 3.5 moles of ammonia? Okay, so we see that there's ammonia plus carbon dioxide is giving you urea plus water. Okay, so the question is, how many moles of urea are formed from 3.5 moles of ammonia? So you use the mole ratios, okay, which are the stoichiometric coefficients. The mole ratio between ammonia and urea. So your ammonia is NH3, which is that one there. Okay, so we are interested in basically that. Okay, so I'm going to highlight those in red so that we see where the mole ratios are. Okay, so it's the mole ratio between ammonia and urea. Okay, so the mole ratio between ammonia and urea is actually 2 to 1. Okay, so 2 moles of ammonia are actually reacting to give you 1 mole of urea. So 2 moles of ammonia are reacting to give you 1 mole of urea. What about 3.5 moles of ammonia? How much urea are they going to give you? Okay, that's the conversion. So basically you're multiplying 3.5 times 1 over 2, which is giving you 1.8 moles of urea. Okay, so this conversion factor is obtained from the mole ratios. These are the mole ratios. Okay, 2 moles of ammonia react to give you 1 mole of urea. So the mole ratio is actually 2 to 1. Okay. So we are still on chemical equations. The law of conservation of mass, for those who attended the first lecture, it says that a chemical equation must have the same number of atoms of a given kind on each side. Okay, remember the law of conservation of mass. It states that matter or mass can neither be created nor destroyed. So when you're looking at your chemical equation, you have the same number of atoms on the left-hand side and the right-hand side, because matter can neither be created nor destroyed. So in this case also, a chemical reaction cannot create or destroy, okay, any given atom. Okay. So let us look at these two examples of these chemical equations. Hydrogen plus oxygen giving you water. Okay, when you look at this chemical equation, it's not balanced, meaning it's not obeying the law of conservation of mass. Okay, you need to have the same number of atoms on the hand side of the equation and on the right hand side of the equation, because the chemical equation cannot create or destroy any given atom. Okay, so meaning chemical equations must be balanced. So we are able to see that on the left hand side we have 2 atoms of hydrogen. On the right hand side, so we are looking at the first reaction. There are 2 atoms of hydrogen, 2 atoms of hydrogen on the right hand side. But when you come to oxygen, we have got 2 atoms of oxygen on the left hand side, but 1 on the right. That is what makes this equation not balanced. So if you have to balance this equation, you introduce a stoichiometric factor of 2 in front of hydrogen gas and introduce a stoichiometric factor of 2 on water. Then you are going to ensure that you have got a balanced chemical equation. Okay, please practice how to balance chemical equations. So looking at a balanced equation, for example, aluminium plus oxygen giving you aluminium oxide. So if you have got, and you have those stoichiometric coefficients, we have got 4 on aluminium, 3 on oxygen, 2 on aluminium oxide. What does that mean? Okay. That basically means that it basically means that there are two ways in which you can explain this equation. One would say 4 aluminium atoms are reacting with 3 oxygen molecules to produce 2 molecules of aluminium oxide. Okay. Another person would say 4 moles of aluminium are reacting with 3 moles of oxygen to produce 2 moles of aluminium oxide. Both are correct. Okay, both are correct. Okay, so we're still trying to understand balancing of chemical equations. Okay, when you're balancing chemical equations, you are basically saying the same atoms must be present in a reaction at the beginning and at the end of the reaction. So if you look at this equation, potassium chlorate giving you potassium chloride plus oxygen. The first reaction here, this first reaction equation is not balanced, because when you look at the left-hand side of the equation, we have got 3 atoms of oxygen, and on the right-hand side of the equation, there are 2 atoms of oxygen. So meaning it's not a balanced chemical equation. So one would attempt to put 3/2 on oxygen. Okay, 3/2 on oxygen. So when you introduce 3/2 on oxygen, that would be, a better way, but you are using a fraction, so it's not the best. Okay, but when you just introduce is balanced, and the best way